Welcome to the Explainer. Today, we're diving into what's basically a high-stakes game of molecular clue. We're going to explore how AI is becoming a master detective, figuring out the exact chemical makeup of a substance just by looking at its unique fingerprint. Get ready, because we're about to see how machines are learning to solve some pretty complex chemical mysteries.
Okay, let's get into it. Before we unleash the AI, we really need to understand the mystery we're trying to solve. And it all begins with the molecular formula. The easiest way to think about it is like a recipe for a molecule. It tells you exactly which atoms you need and how many of each, but it doesn't tell you how they're all connected. To get this recipe, scientists use this amazing tool called a mass spectrometer. It's like a hyper-precise scale that gives us the clues we need to figure out those exact atomic ingredients.
So, here's how we're going to break this all down. First, we'll lay out the problem we're up against. Then, we'll meet our three AI detectives, FIDDLE, MEDUSA, and a more classic machine learning model. We'll see how they stack up against the old-school methods, and by the end, you'll have a clear roadmap for how you can join this investigation yourself.
First up is FIDDLE. It's a deep learning model that specializes in a technique called fragmentation. You can honestly think of it as a molecular CSI, analyzing the tiny pieces left behind after a molecule is deliberately shattered into bits. Imagine shattering a beautiful crystal vase and then trying to figure out its original shape just from the shards. Well, that's exactly what FIDDLE does. It takes this chaotic mess of fragments you see on the left, that jagged, spiky pattern, and uses a neural network to piece it all back together, revealing the original, elegant molecular formula on the right. It's pretty amazing. Now, here's where the real magic happens. The AI doesn't actually see that spiky graph. Instead, all that data gets translated into a language it can understand, a long string of about 7,500 numbers called a vector. Think of it like a unique barcode for the molecule. The AI also gets a few other key clues, like the molecule's original weight and exactly how much force was used to break it. And here's the really brilliant part. FIDDLE doesn't just give you one single answer and say, that's it, no way. It gives you a lineup of the top 5 suspects, and each one comes with a confidence score. For scientists, this kind of probabilistic answer is way more valuable than a simple yes or no. This slide basically shows us the brain behind FIDDLE, and it's a convolutional neural network, or CNN. It's a total pattern-finding machine. The first layers are like using a magnifying glass, spotting all the tiny little details. Then the deeper layers are like a wide-angle lens, seeing the whole bigger picture. Once it has that complete view, a final layer comes in and just counts the atoms. This many carbons, this many hydrogens, and so on. So what's the final verdict on FIDDLE? Well, it's a speed demon, about 10 times faster than his competitors, and it's a real pro at identifying unknown molecules. But it does have an Achilles heel. It gets a little flustered by noisy data, and it can get stumped if it runs into rare, exotic elements. Okay, now let's meet our next detective, MEDUSA. If FIDDLE is the specialist you call for a single, isolated crime scene, MEDUSA is the master of crowd control. It tackles a much messier problem, identifying a bunch of different molecules all jumbled up together. So instead of looking at shattered fragments, MEDUSA surveys a whole crowded room of intact molecules. It sorts through all the chaos you see on the left by focusing on each molecule's unique isotopic signature. You can think of it like a subtle accent that gives away a molecule's true identity, even in a really noisy crowd. But before MEDUSA even gets to work, the data has to go through a critical cleanup step. See, the raw signal has the main molecule, sure, but it also has a series of echoes from its heavier isotopes. So a pre-processing step called de-isotoping comes in and gets rid of all those echoes, kind of like a sound engineer removing feedback. This gives the AI a nice, clean signal to work with. And this is what makes MEDUSA so special. It doesn't just give you a single, concrete answer. It provides a confidence interval. It might say something like, look, I'm pretty sure there are between 5 and 7 carbon atoms here. And this willingness to embrace ambiguity is a total game changer for scientists who are dealing with messy, real-world data all the time. The engine driving MEDUSA is a recurrent neural network, or RNN. Think of it like this. When you rate a sentence, the meaning of a word depends on what came before and what comes after, right? So you kind of read it forwards and backwards in your head to get the full meaning. MEDUSA does the exact same thing with the spectral peaks, getting the complete picture before it even tries to identify the elements. So MEDUSA is a true pioneer. It's capable of discovering brand new formulas hidden in complex mixtures. But it does have a bit of a perfectionist streak.
It needs pristine, high-resolution data to work its magic. And because it's trained on simulated data, it can sometimes get confused by the pure unpredictability of real-world samples. All right, let's switch gears completely. We've seen two AI models that are true detectives, right? They go out and solve the mystery. Our next tool is, well, it's more of a judge. It's a classic machine learning model that doesn't find the suspects, it just evaluates the evidence against a lineup it's already been given.
So yeah, this model is a judge, not a detective. It's given a peek from the data, and it's given a list of possible formulas. Its only job is to weigh the evidence and assign a probability of being correct to each suspect in that lineup.
Now, this classic approach is a reliable workhorse. It's fast, it's transparent, especially on familiar territory. But it has a fatal flaw. It's totally stuck in the past. It can't handle new types of data, and it is completely incapable of discovering anything new. It's a score, not a seeker.
Okay, so we've seen the new AI contenders and the old school champion. Now it's time for the main event, a head-to-head comparison. How do they really truly stack up? It all really comes down to a fundamental trade-off. You could call it street smarts versus book smarts. The AI learns from experience, from seeing tons and tons of data, so it thrives in the chaos of the real world. The classical approach, on the other hand, follows a strict rulebook based on physics and chemistry. It offers perfect clarity, but only in a controlled, squeaky clean setting.
And let's be crystal clear. In some cases, the classic approach is still king. I mean, if you have absolutely perfect data from a simple molecule and you need to be able to show your work step by painstaking step, well, then the old school method is still unbeatable.
So, you've seen the battlefield. You know the players. Now you're probably asking, okay, what's next, and how can I get in on this? Let's explore the exciting frontier of this field. This roadmap lays out a really clear path, especially for anyone with an AI background. In just 6 months, you could go from being a chemical novice to a pioneer who's building their own research prototypes. And this isn't science fiction, it's actually a very accessible field. And to get you started, here are 3 fantastic little bootcamp projects to sharpen your skills. You could build a simple score in just a day, a basic atom counter in 3, and an uncertainty model in 2. These are really hands-on, high-impact ways to master the core concepts. So what's the bottom line? AI models like FIDDLE and MEDUSA are revolutionizing how we identify molecules. The future isn't about AI versus classical methods. It's about combining AI's incredible pattern-matching power with the rigor of traditional science. A whole new era of automated chemical discovery is dawning, and the door is wide open for you to help build it.